Us. So we're gonna start around 8:05. Just gonna let some people get here. So just get situated, and yeah, we will start pretty soon. Sorry, I think I just choked on the air a little bit. So yeah, whoops. All right, it is 8:05. Let's begin then. Alright, so let us start. Sigma notation. Alright, so just a quick little review of what is happening with sigma notation and how it works and stuff. Okay, so we have a few things going on here. First, this entire thing has a name. This is called a summation. And then we have this little part in here. This is called the summand. And this A and this B and this K, this also has another name. It is called the index. Plural indices. But yeah, so I'm going to use those terms to refer to things here. So just make sure that you're aware of what those all mean. Okay, so what sigma notation does is you take the summand, and then you see this little subscript over here, that's the index. So it starts wherever the index is, and then you add 1 to it, and then 2 to it, and then just keep going up until you finally get to essentially the endpoint, which is up here, B in this case. So let's look at this and expand this summation. So this thing is our summand. It's tangent of stuff. And our index is over here. It is F. And it starts at actually -2. All the time you'll see them start at different places, usually like 1 or 0 or something. But here it's going to start at -2. It doesn't really matter. So we know what it says. We know what we're going to do. So let's do it. So it's going to be tangent of, so the F starts at -2. So that'll be 2 times -2, which is -4, plus 1, which is going to be -3, and then pi over 4. And then tangent of, that's going to be -1. So 2 times -1 is -2, plus 1 is -1. So -pi over 4. And you can probably start to see the pattern that's going on here now. Just adding 2 to the coefficient of pi. So next we have tangent of pi over 4 plus tangent of 3 pi over 4. We're not quite done yet. This is going to give us 5 things. We have 4 right now. So you go 1 more, and then you should end up with... let's see. So we get 0 and then, oh, I think we actually have more. Okay. So hold on, let me just make sure that I did that correctly. So when that's 0, yeah, so this is when we have -2, -1, 0, 1, 2. Okay, so this is going to be 2 times 2 plus 1. So that's 5 pi over 4. And then the next one is going to be when you have F equals 3. So that'll be plus tangent of 7 pi over 4. So there's a question in the chat that asks, on the test, do you want us to simplify it? I'm assuming it is referring to the summation. If I say expand, all I'm looking for is this. Okay, so I'll let you kind of process that a little bit. But essentially, if you just start to see the pattern, then it's really easy to just go on and do that. So take a picture of this or something, and then I'm just going to continue on, mostly for time's sake. Okay, so writing a summation from the given pattern. So now let's look at what's actually happening so that we can write it into a summation. So what is happening here? We have 1 over 3, 2 over 9, 6 over 27, and then 24 over 81. and then there's alternating between positive and negative. So what's happening here is we see that there's alternating. So we know that we're going to have -1 to some power. Because what's happening there is if you start with k equals, I don't know, something, like 1, then you're going to have some sort of power here. And then you're going to, we want +1 multiplied in front here. And then the next one, when we add 1, then you're going to actually get a -1 because you're going to go between odd and even. Odd and even powers of this are going to give +1 and -1. So let's look at what's happening in the denominator. So the denominator is 3, 9, 27, 81. So what you will be, if you've had enough experience with this stuff, you'll be familiar with that and know that this is just the powers of 3. So this is 3 to the first power, this is 3 squared, this is 3 to the third power, and 3 to the fourth power. So if we're starting with k equals 1, then it'll be clear that somehow we're going to have an over 3 to the power of k, because k starts at 1, so 3 to the 1, that's the first thing that we want. I'll make that a little bit more, because we know that we're going to have that -1 as well, to some power. Okay, so what's happening on top? 1, 2, 6, 24. If you look at how those are arranged, you'll start to notice a pattern. We actually went over this in the beginning of the year. This is called factorials. So this is 1, this is 2 times 1, this is actually 3 times 2 times 1, and this is 4 times 3 times 2 times 1. So what we're going to get then is k factorial. And then if we look at this power, what that's supposed to be, we want, if we start k equals 1, we want this thing to be positive first. So let's just add 1 to it, so that this becomes -1 to the power of 2, which just gives us +1. Okay, so where is this going to stop? Well, we know that 3 to the k, if we do 3 to the fourth, that's 81. So maybe it's 4. Let's check that for k factorial. So does 4 factorial equal 24? It's 4 times 3 times 2 times 1. And yeah, so that'll be 4 times 6, which is 24. So that checks out. And that is this thing. So notice what I was doing here was just looking at there's patterns. What are those patterns? How do they look? And how do we understand those things? So yeah, we saw alternating. We saw denominator as powers of 3. And then numerator is just factorials. Okay, so now let's move on to the next one. And again, let's look at patterns. What patterns are happening here? So we have 2/3 in every single term. So 2/3 is a factor, since it's in every single term. And then we have f of 1 plus something. 1 plus something. So it looks like there's something with a 3, and then there's some numerator. They're all even. So we have 2, 4, and then we go to 14. So if they're even, then that means they're all divisible by 2. So that means we just multiply something to those. And the question is, what is that? So we see that we're going to have 2/3 f of 1 plus something times 2/3. So the first thing is we get 2, then 4, and then continues until 14. So it looks like it's possible then that this is going to somehow get just even numbers. 2, 4, 6, 8, 10, 12, 13, 14. That's 13. 2, 4, 6, 8, 10, 12, 14. So this would be 2 times 1, 2 times 2, and then this would be 2 times 7. So that would make it so that our k could start at 1, and then it'll go to 7, and that means the number that gets multiplied in front there is just k. Alright. So again, just reviewing the pattern, we saw 2/3 is a factor, so 2/3 is going to be multiplied to everything, and then we have f of stuff. It's 1 plus even number over 3. So we were able to see that it was 2, 4, and then 1 up to 14. So we know that with that, this is not going to be powers of 2. Otherwise, 14 would not be in there. It'd be something like 16 or 32 or 64, but that didn't happen, so it gives us the hint that we have just even numbers increasing to 14, from 2 to 14. Alright, so now let's apply this stuff, and this might look kind of familiar actually, to area under a curve. So let's look real quick at why we would even want to do this in the first place. So the area under a curve tells us a few different things. It tells us something related to slope. So slope itself tells us rates of change. So how fast is a function changing? And then the area tells us what happened through that change. So in a physical sense, what that means is if we're looking at, let's say, speed of a car, speed is a rate, which is a slope. It is the slope of the position function, actually. And if you find the area under the velocity curve, what that tells you is how much distance you covered as a result of the change that you had. So approximation is what we're going to be doing. Because we don't know calculus, so we're not going to be able to get the exact number. So yeah, let's just look at some stuff that we can do here. To approximate this, we can just use a bunch of rectangles. So if you just had, let's say, 1 rectangle plus 2 rectangle, very easy rectangles, that'll estimate the area. Not really great, but it estimates it. So let's look at some of these things. So let's use 4 rectangles and see what we get. So if we have 4 rectangles over here on the left-hand side of each interval, then we see some interesting stuff happen. So left-hand endpoint. So what's the base? This is going to be some distance divided by 4. So what is that distance? Well, if we take b minus a and divide it by 4, then what we're doing is we're getting all of these, this entire area, or line, that distance dividing it to 4 equal pieces, so that means each of these is just delta x. Well, that thing. So there's a special thing called delta x, so it's just change in x. And yeah, so we don't know what that is necessarily because we don't have an A or a B. There's just a general case to show the idea of what's going on. Okay, so let's look at the height then. We notice that the height actually touches the function. Oh, that's interesting. What does that tell us? Well, that tells us this is f at a. This is f at a plus delta x. This tells us f at a plus 2 delta x. And then this tells us f at a plus 3 delta x. So what's happening then is we have f of a plus delta x times something. So let's just say that's times k. So at first this starts at, k would be 0, right? So from k equals 0 to k equals, so that's going to be 3. So just leave it like that. Make it a bit easier. Okay, so let's turn that off and look at right-hand stuff. So on the right hand, we see we have these things going on. Oh, whoops. Turn that off. Oh, they're on the same layer. Whoops. Oh, well, anyway. So I'm just going to turn it off for now. So this less distracting. I'll put them both up later. Anyway, so here we see, I guess we can turn that on and see that the same distance as delta x, right? So the base is still delta x, just like in the other one. And then the height, same exact idea. This thing is still touching the curve. It's just at different times. So this is going to be f at a plus delta x. And then this is f at a plus 2 delta x. And then f at a plus 3 delta x. And then now, the only difference then is it ends at f plus 4 delta x. So we're going to have f of a plus, let's just say k delta x again, from k equals 1 to k equals 4. Okay, so notice that k is going to end at 4, and that's how many rectangles we have, right? And then here, k ends at 3, it's going to be that minus 1. So we can generalize this to get an equation. And this is what we get. I'll erase that so we can see. Or that. Okay. Oh, wrong layer, that's why. Okay. Doing it live. Okay, so if we have a number of rectangles, let's just call it n. And then delta x, that's just the distance between each little sub-interval like that. Then we can say L sub n. L sub n represents left-hand endpoints. R sub n represents right endpoints, when n is just the number of rectangles that you have. So notice that they're almost exactly the same. The summand is identical, just the indices are different. You could also go the other way around and make it so that the summand is different, but the indices are the same. In a calculus class, you actually want to do that. You'll see why later on. Actually, we'll do that this year later on. And if you take calculus later on, you'll see why again. Alright, so let's move on. Alright, so over here we have this little graphic organizer that we've worked with for the past about a week or two-ish. Actually, just 1 week. But anyway, so definition, how to find algebraically, why you can find it that way. So, domain, range, x-intercept, y-intercept. I'm just going to quickly go over exactly what these things are and why they work the way that they work, just so that we can get some quick review right now real fast. So domain, that just tells us what's able to be put into the function. So you can kind of think of it as the default domain. So looking over here, default domain is all real numbers, but certain values will make a function undefined. Not all functions, but some functions. And then we can just remove them and say that the domain is everything except for whatever that is. Which is why, to find it algebraically, the easiest way to do that is just find where the function is undefined, and then exclude that from the domain. So essentially set the denominator equal to 0. And notice that you're going to do that for both domain and vertical asymptote. Because in one of them, you're trying to figure out what's undefined so that you can remove it. And in the other, you're trying to find out what's undefined so that you can use it in the function, because that's what it's going to be. So, range. That's a set of all possible outputs So essentially you can graph it. That's one of the easier ways to do it if you can't find the inverse of the function. And so inverse, let's just talk about that real fast. If you have two sets, x and y, x goes into y, and the way that it does that is through f. And then y goes into x. So things from y turn into things in x, and there's like an exact one-to-one mapping there through something called f inverse. So that's kind of like the, in a way, reverse of f. So what you can think about then is it's easier to find the domain of something, and the domain will essentially be the set. So notice that these are two sets. This can be the set from which a function is leaving. So for f, x is the domain. For f inverse, y is the domain. So that means the domain of the inverse is the range of the original function. So let that sink in a little bit. Alright, so moving on now, just for the sake of time. X and y intercepts. I'm going to cover them both together right now because they're very much related. So x and y intercepts. We're basically trying to figure out where does the function intersect with one of the axes. So either the x-axis or the y-axis. So in other words, we're going to try to figure out where it equals whatever equation that is. So, also their coordinates. So make sure you know their coordinates. The x-axis is a line. The y-axis is a line. The equation of the x-axis is y equals 0. The equation of the y-axis is x equals 0. You can think about why that is. Essentially, just look at all the points that are on the x-axis. Look at their coordinates. Look at the coordinates of everything on the y-axis. You'll see that y equals 0 for everything on the x-axis, and x equals 0 for everything on the y-axis. Which is why you can just set the y to 0 and solve for x for an x-intercept. And set x equal to 0, solve for y a y-intercept. If you forget that, just look for, you're solving for x-intercept. You want an x. You don't want to set it to 0. That doesn't make any sense. Because you already know what x would be then if you set it to 0. And you solve for y y-intercept. You don't want to set y to 0 there because that's also not going to make any sense, right? Alright. So now let's go on to vertical asymptotes and horizontal asymptotes. So, well, I'll cover vertical first, alone. Alright, so vertical asymptotes, by definition, it's the vertical lines that represent where the function is undefined, and specifically when it's not a removable discontinuity. That's the next thing we'll go over, so don't worry if you kind of forgot what that was. So, find where the function is undefined, set the denominator to 0. We want to find where it's undefined, right? So just set denominator to 0, if you have one. If you don't have one, then you kind of can't get undefined anyway. Like if you have a parabola or a cubic function or something like that. Alright, so yeah, why that is literally just because dividing by 0 is one of the ways for a function to be undefined. In this unit, that's the only way functions will be undefined. Okay, so horizontal asymptote and end behavior, they're basically the same thing. The thing that's different about them is horizontal asymptote talks only about convergence. So I guess the lack of horizontal asymptote would tell you that there is no convergence. Versus end behavior tells you both of those. It's just a statement that explicitly says that. As opposed to horizontal asymptote, it's just a line that represents the existence or lack thereof of convergence. So remember, degree is basically just the highest power. So if you had something like x to the 7th power minus x cubed plus 2x minus 1, the degree is 7. So, deg, that's short for degree here. Degree of the numerator and the denominator, you're just going to compare those two. And if the one in the numerator is less than the denominator, horizontal asymptote is y equals 0. And if it's reversed, then there is no horizontal asymptote, and the end behavior tells us that as x approaches positive and negative infinity, y will approach either positive or negative infinity, depending on the way that the function works. We'll see that later on. And then the degree of the numerator and denominator being the same tells us that we're going to have y equals the ratio of leading coefficients for the horizontal asymptote, and then y is going to approach whatever that is in its end behavior. The reason for this is degree tells us about growth rate of functions. If a function is growing, so let's say we have a function like x plus 1 over x squared minus 2. So here we see the numerator is growing a lot slower than the denominator. The denominator is going to get really big really fast. The numerator will not. It'll get big but not as fast. So then this is going to start approaching 0 because you're going to get small number over gigantic number eventually. So if you kind of think about the chances of winning the lottery, let's be real, that's, yeah, pretty much not going to happen for any of us. Then, yeah, that's going to basically approach 0 because like you put in one ticket out of like a million or something. So think small number out of big number. So now what if we reverse that? Let's just say that's cubed up there. Then we'll end up with something a little bit different. The numerator is going to be growing a lot faster this time. So instead of going towards 0, the exact opposite is going to happen. This thing's going to get infinitely big. This is going to be going toward infinity. Therefore, there is no horizontal asymptote since infinity is not a number, so you can't really converge toward it. So, what if they are the same? And let's just make it so this is 2 and this is 3, just so that we can kind of see that a little bit better. So, growth rate of x squared, and then you multiply by 2. Growth rate of x squared, you multiply by 3. Realistically, let's look at this and think about it. The plus 1 and the minus 2 eventually are not going to matter a lot, just a little bit. So, what actually is going to happen is as we let x go toward infinity and let numbers get bigger and bigger and bigger, eventually what's only going to matter is 2 times whatever and 3 times whatever. So this is going to be going toward 2 over 3 instead. Alright, so that's what ratio of leading coefficients means. So we'll see more examples of this as we practice later on. So let's just start moving on and going to removable discontinuities so we can understand that real quick. Alright, so removable discontinuity, this lovely little thing over here. So what is it? First thing is, it's a hole in a graph. By hole, I mean like it's just a little thing that's there. It's essentially a point that's removed. And a vertical asymptote would have been there, but the thing is that thing got removed instead, which is why it's called a removable discontinuity. You will also see it in some places called a hole, because the way that it's drawn on a graph actually is, well, a hole. You'll see what I mean once I start actually doing it. Alright, so let's move on and just try figuring out how to do it. Well, factor. You always want to factor everything that you are given, just in case. And then if you can divide something from the top and the bottom out, chances are that's going to be your hole or removable discontinuity. So let's just look at it and try to make that happen. So here's an example over here. Find the removable discontinuity and the graph. So let's factor this thing. We got x plus 2 divided by x plus 2 times x minus 2. And then we see that the x plus 2's can divide out because it is a factor on top and then a factor on the bottom. In fact, the factor on top is the top. We get 1 over x minus 2. So this is going to be your actual graph. This will be the function. Or I guess you can say this is going to be the graph. So it's going to look like this. However, with x equals -2 removed. So let's figure out what this is going to look like then. So let's find, I don't know, I guess some intercepts and stuff. X-intercept, so we're going to set the whole thing to 0, which means that the top part gets set to 0. That never happens. None. Alright, so y-intercept, let's figure that out. Set x equals 0, so let's see. 1 over 0 minus 2, so -1/2. So 0, comma, -1/2 is our y-intercept. Alright, cool. We're going to have a vertical asymptote. Well, looking at this, we see that if we set x minus 2 equal to 0, so denominator to 0, find where it's undefined, we're going to get x equals 2. That's going to be our vertical asymptote. Horizontal asymptote, let's see. So the degree of the numerator is less than the degree of the denominator, so the denominator is going to be growing really fast. While the numerator, in fact, the numerator is not growing at all. It's just going to be 1 over gigantic number as x approaches infinity. So we get y equals 0. And just for demonstration's sake, I'm going to show the end behavior here and connect that to the horizontal asymptote. So as x approaches infinity, y is going to approach 0. And as x approaches negative infinity, y is also going to approach 0. Chances are they're going to be the same thing. So this number and this number probably are going to be the same. Maybe I should color code that. Anyway, so let's try graphing this thing, because that's in the instructions. Alright, so let's see. Let's make that 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Okay, so if we look at this, we have, let's see, x-intercept none, y-intercept x equals 0, so we have 0, comma, -1/2. So let's just graph that. I'll make that in red. 0, comma, -1/2. And then a vertical asymptote at x equals 2. So let's do that. Y equals 0. Okay, so we see that we have this thing. And then now let's look at the point that got removed. We have x equals -2. Let's plug that into this function. So the final form. So we got 1 over -2 minus 2, which is -1/4. Sorry, just noticed that it wasn't not showing, so there we are. 1 over -2 minus 2, -1/4. So if this is the x and this is the y, then we have a removable discontinuity at -2, comma, -1/4. So I'm going to do that in... I'll do it in blue. So there, I'm going to label the point -2, comma, -1/4. and then just do the graph in white. Or yellow might show up a little bit better because of the contrast. Alright, so functions are going to go toward the asymptote. And then if you want to get accuracy up here, you could. X equals 3 is going to give us, let's see, 1 over 1. So then we would get this as our graph. And notice that we just have that little circle there at -2, -1/4. That's why it's also called a hole. It's because it's literally drawn as a hole. But just the name hole doesn't tell you a lot. Removable discontinuity tells you a lot. Alright. Moving on. Actually, take a picture or whatever if you need to real quick. I'll give you like 15 seconds and then we'll move on to the next thing, which is going to be review on linear transformations. Alright, moving on. Linear transformations review. Whoops. Okay, something like that. There. Alright, so let's say that we have a function f of x. And we have another function y. And the function y is a linear transformation of f of x. And it's in graphing form. This is what graphing form means. The reason it's called graphing form is because it's actually easy to graph once you have it in that form. Because of linear transformations. So the term linear tells us that if you do something to a system, the same thing happens to everything within that system. So if you think about easiest example of a linear transformation that people will see in real life is guitar capoing. So, or bar chords. So you might not know what a capo is just by name, but if you've ever seen a guitar and a guitar player, it's that little clippy thing that they put onto the guitar. If you put it at a certain fret, that means every single string moves up by a certain number of notes. That's basically what's happening. That's called a linear transformation. So if you think about it that way, each of these values then, these are called parameters, they're going to do something to every single number in a function. So parameters for scaling. So there are two different types of transformations. There's scalings and translations. Scalings means transformations by multiplication, and parameters means translation means transformations by adding or subtracting. So I'll just write that real quick over here. So multiplication or division, and then addition or subtraction. Because scaling, that just means like if you scale something up or down, you're not adding anything to it. You're multiplying by it. That's why when you think of the term like something is drawn to scale or something like that, that tells you that there's multiplication related to it. And then translation, what that means is you're translating stuff. You're moving things over, up, down, side to side. So that's just adding or subtracting x and y values. You can think about it that way at least. Alright, so how do parameters affect the function then? So the first thing is that you're going to want to get some reference points. So quick example over here, if you have the sine function, you're going to want to probably find the roots, so you know the x-intercepts, the min and the max, as your reference points. Because if you do something like this, so the 0 points, the min, and the max. Once you have that for sine, it is really easy to graph, right? Just connect the thing, And yeah, that's basically the sine graph. If I were actually trying, it would be a lot better. But anyway, so let's move on. So get those reference points, and essentially what you're doing then is you're transforming those reference points through the things that we're doing with the parameters. So let's look at what each parameter actually does and what it means mathematically then. Alright, so A, what it does is it does a vertical scaling. So in the past I've said vertical stretch or shrink. I'm just going to say vertical scaling because it's going to make things a little bit easier and a bit less confusing. So it is a scaling of some sort by a factor of A. What that actually means is you're multiplying all the y values by A. So if you think about that, it actually should make a lot of sense because I'll scroll back to this, don't worry. If you look at graphing form, A is being multiplied to everything. A times stuff. That stuff is an output, right? Because the inputs are inside here, right? So you're multiplying A to the outputs. In other words, A is being multiplied to all the y values. So it only makes sense then to multiply A to every y value, because that's literally what you can see happening. Okay, so B, this is a horizontal scaling. So horizontal refers to x values, right? So you're dividing all the x values by B. Okay, so you might be thinking, wait, why dividing here? So if we look over here, B times x. So what's really happening is you're multiplying every x value by some value. And then you're applying the function to it. So in a way, you're taking like, if you did like 2 times x, then you're getting values that are 2 times bigger and bringing them earlier. Because at the time where x would have been 1, it is now x equals 2. The place where x would have equaled 2, it is now x equals 4. So everything is compressing in a way, or stretching if you're using fractions. Fractions less than 1 and greater than 0. Okay, so that's why essentially the function's compensating for that by just dividing by b for all the x values. So that's probably the most, or the least clear one out of those. But once you kind of get that concept, or just memorize this dividing, just for now, it's actually something that makes a lot of sense. Alright, so H. This is a horizontal translation by H units. So if you just add H over B to all your x values, that's going to work out perfectly. Notice that throughout all of this, I did not say anything about if you have negative in front of the function or for B. So I've never talked about that. The reason for that is with this mathematical interpretation that we have over here, if you're just adding H over B, if B is negative, then it'll already make up for that in there. So you'd have something over negative, I don't know, like negative 1, negative 2. So if you're adding that, you're just subtracting. Unless H, of course, is also a negative. Alright. And again, let's look at that real fast. It should make sense because you're taking H away from the x value before applying it. So same idea, the function is in a way compensating for the fact that that's happening before it does anything. Okay, and in K, this is also very simple to see. So vertical translation by K units, adding K to all y values. If you look at this, you just have a thing, and these are y values. We've already established that. Then you just add a K to all of those, and then there you go. So A and K are really easy to understand just by literally looking at the function and thinking. B and H, you kind of have to think about what is the function even doing, what's the function even, like what is it, and then it makes a little more sense after that. Okay, so what I want to do right now then is give us some practice time. So here are the instructions for all the things that we have. So you're going to identify domain range x and y intercept, vertical asymptote, horizontal asymptote, and end behavior, then graph the function. And then what you want to do is identify the transformation if all the transformations if the function is a transformation. So what I'm going to do is give us about 7-ish minutes on each of these. I think I have 3 or 4 problems here. And then after that, I'll just go over it. So I want you to practice this. So if you're watching this and it's not during the stream, then yeah, you can always just like pause it, skip it, or whatever. But yeah, so I'm going to start the timer for that right now. I'll put 7 minutes on the clock, and then I will come back. And right now I'll just still be at the computer. So as you're doing this problem, I'll just be there. If you have questions, put them in the chat. Alright, 7 minutes. I'm putting that on the timer and starting it right now. Alright, about 10 seconds and then we'll get back together. Alright, so let's look back at this and I'll just go over it a little bit. Then we'll go into another one after this, and then, yeah, I think there are 3. Alright, so first thing we should always do is try to factor whatever we have. So let's see, what can we take out of this? So let's see, there's an x in common. So let's take that out. Oh wait, that's just supposed to be an x, not an x squared. Okay, so what can this... So we need something that will multiply -8 and add to 2. So if we have plus 4 minus 2, that works. Okay, so after we do that, we can figure out the other stuff. Alright, domain. This is a polynomial. It's parabola-ish. Oh wait, no, it's not parabola. It's a cubic. Because of the 3. So this is going to be a cubic function. It is going to not have any asymptotes or any undefined points. Therefore, the domain is all real numbers. So you can say that the domain is... Remember, the set of x such that x is in the set of all real numbers. Ooh, whoops, that was weird. Clicked the wrong button. Okay, sorry. A little malfunction there. Alright, anyway, so... let's figure out the range a bit later. Although if you know how this function is going to look, you already know what it's going to look like. What the range is going to be. Okay, so let's look for the x-intercept. So set the whole thing to 0. So let's set the factored form equal to 0. And then let's see. So if any of these is 0, then we get 0. So if x is 0, if x plus 4 is 0, and if x plus 2 is 0, then we get that the whole thing is going to be 0. So what makes that happen? X equals 0. S equals -4. And s equals 2. So the coordinates are 0, 0, -4, 0, and 2, 0. Alright, so y-intercept, let's look for that thing. So that's when x is 0, so y of 0 equals... So it's going to be 0. You can easily tell because all of these is going to be 0. So you just get 0. So 0, 0. That thing happens to actually be, well, what's it called? An x-intercept and the y-intercept at the same time. So that's kind of cool. Alright, so vertical asymptote. Due to the domain, that already tells us that there are going to be none. How about horizontal? So this is a cubic function. We know that it's going to look something like this or like that. That's not going to converge to anything. And also, I guess if you think about it another way, this kind of has a denominator. It's just 1 divided... it's just divided by 1. Degree of a constant is just 0. So then that's just going to tell us that we also have none. So let me write that correctly. None. So the end behavior. This is going to be a cubic function. This is going to be a regular cubic function. So that's because we don't have a negative in front of the x cubed. So we know it's going to look something like this. If you don't know that immediately, you can always start graphing it, then you'll see. So the end behavior, you can write it as x approaches infinity, y approaches infinity. And as x approaches negative infinity, y is actually going to approach negative infinity. So that's what we see here. Approaching infinity, approaching negative infinity. So let's do the graph then and see what this thing looks like. Okay, so let's see. We end up going to 4 at one point. So what you can do is, let's just go by ones the entire way. 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh. Interesting. Oh well. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then going 9 yet again. I think that's probably actually 10, because that's not symmetrical. Anyway, let's just 1 to 9, 1 to 9, negative 1 to, I guess that's negative 10. Doesn't really matter too much, just make it work somehow. Oh, so there was a question about whether you need to write the end behavior this way on the test. Yes, because that's how end behavior is properly written. So, yeah, just clarifying that. Good question. All right, so let's start graphing this thing then. All right, so x-intercepts, we have 0, 0. We have negative 4, 0, so negative 1, 2, 3, 4. And then 2, 0. All right, so quick thing I want to go over is the multiplicity of these things. These each have multiplicities of 1, right? Actually, I shouldn't use yellow because I've already used it for something else there. Multiplicity of 1, because they all are raised to the power of 1. Therefore, we know that the function is going to go through each of them. So, hold on, just quick thing. All right, just need to take care of one quick little thing. So we can essentially see that because we know what the function is going to look like, we can kind of sketch this graph. And that's more or less what it's going to look like. That's kind of all you really need in order to know what the function is going to be. And yeah, so looking at that, you'll be able to see that the end behavior is this thing that I did right. Okay. So I'm going to give us a little bit of time to just process that, and then we'll move on to the next one. So about like 30, 45 seconds, and then we'll move on to the next thing. Alright, so I'm going to move us on to the next problem. And again, it's going to be 7 minutes. Or work on this, and then I will check back with this, and I will see how it looks. Alright, so 7 minutes on the clock. And I'm going to begin that right now. Oh, by the way, so if you're not completely done with the previous problem, I would suggest don't worry about it right now. Just move on to this one. and try to do it as quickly as you can. So timed practice, that's always a good thing because then you get used to going through things. All right, so 7 minutes, let's begin. As you work on this, there was a question in the chat asking the difference between even and odd multiplicity. I'll just do that on the screen real fast with this. So if you have something in factored form like x plus 1 cubed times x minus 1 to the fourth times x plus 2, I don't know, squared. Even multiplicities, those are just even powers. Essentially, the function is going to hit those, the x-intercepts related to those, and then bounce off the graph, rather than this one, for the odd multiplicity, just going to go through. So just a really quick sketch on this. So -2, -1, and 1. So going to go through at -1 and going to bounce off at the others. So let's see, the y-intercept's going to be 4, 0, 4. So I don't know, 4, something like that. So we know that this thing has to go toward the function, and toward the x-intercepts. Then it's going to somehow bounce that hit that bounce off. Okay, so this is not this. It's just explaining even and odd multiplicity, just kind of ad-libbing it. Okay, so when the actual thing, the time goes up, I'll erase that and then go over the rest of it. All right, so I'll answer any other questions during this time as well. quick thing before time is up. One of the questions in the chat was about range. Oops, forgot to do that on the last one. Basically, you graph it, you see the range there. I'll do that right after time goes up. Alright, so time just finished, so a few things. I'm going to just get rid of this, and then I'll talk about the range for the previous one. I keep forgetting to do that when I'm teaching. Okay, so range. That's the set of possible outputs. So if we look over here, essentially what we will get is, look at the graph. What are the possible y values? It goes on infinitely. There's nowhere where the function is breaking at all in terms of the y's. So the range in this case is also going to be all real numbers. Is that always going to be the case? No. So should you just guess the range as all real numbers or the domain as all real numbers most of the time? No, please don't ever do that. Don't just guess it as that, because chances are you'll be wrong. Yeah, just don't. But essentially, if you know how the graph looks, you can probably find the range pretty easily. If you don't, then it's kind of hard. So learn how to graph, be competent at graphing, and yeah. Okay, so let's look at this. This one is going to be actually pretty easy to graph because this is a transformation. So the parent function is f of x equals 1 over x. Okay, so what's happening to this? Transformations. What we have is, this is basically 3 times that thing. So that's going to be like your a value. So this is vertical scaling by 3. And then let's see. Next thing is b. That's going to be the thing multiplied by x. So, or multiply 2x, 1/2 times x. So, I'm also going to write here what we do to it, to the values. So multiply y is by 3. Okay, and then this 1/2, there's a horizontal scaling by 1/2. So that means divide x's by 1/2. In other words, multiply by 2. And then at -1, that's going to be a horizontal shift, or you can say translation. I'm just going to put shift because it's shorter here. Shift. So, okay, it's h over b. H here is positive. 1 over 1/2. So 1 over 1/2 gives us 2. So since it's 2, and that's positive, it's going right. So add 2 to x's. And over here, you add 2. Okay, so that's going to be a vertical shift 2 up. So here, add 2. Add the number 2 to the y's. Okay. So we can actually just graph that real fast, and that should help us with finding the rest of it as well. And I'm just going to do the whole reference points thing that I talked about up there, just because it'll be helpful to go over that. So what I like to do is go by scaling first. So I'll put the reference points up here in yellow. Actually, blue is a little more contrasting. Reference points. So what we know about this function is there are no intercepts. However, 2 points that are kind of like the pivot points are 1, 1, and -1, -1. And then we have vertical asymptote at x equals 0, horizontal asymptote at y equals 0. So let's do that. Scaling. So multiply all of the y's by 3. That includes the asymptote. So multiply all the y's by 3. So we have something comma 3, and then something comma -3. And then vertical asymptote is going to be, well, that's not affected yet. Horizontal asymptote, y equals, okay, so multiply that by 3. Well, that's still 0. Okay, cool. Alright, divide the x's by 1/2. So that means multiply all the x's by 2. So 1 divided by 1/2 is 2. -1 divided by 1/2 is -2. And then vertical asymptote, 0 divided by 1/2. Well, that's still 0. And then by translation or shift, let's transform these points. So gonna add 2 to all the x's. So that's gonna be 4 comma stuff. And then add 2 to that, we 0 comma something. And then vertical asymptote was x equals 0. Add 2 to all the x's. Vertical asymptote is now x equals -2. And then now we can look at our other things. So the y's, what we do is add 2 to all of them. Okay, cool. So we get 5, -1, and then 2. Alright, so graphing that real quick then, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm just gonna go to 9 all around. Whether or not it actually is 9. Okay, so let's look at our reference points and our asymptotes. Asymptotes, let's just graph that first. X equals -2. Wait. Oh, no, that's +2. How did I get negative? Sorry, I apologize for that. That's what happens when you talk and write at the same time. Sometimes random marks end up happening in places where they probably shouldn't. Okay, so there's our asymptotes. And then let's see our reference points. 4, 5. 1, 2, 3, 4, 1, 2, 3, 4, 5. Alright. And then we have 0, -1. So 0, -1. Right there. Then we can draw our approximate graph right there. And then, oh, hey, look, it's convenient to know what the, what's it called is, the intercept. So let's just start finding the other stuff. So, domain. If we look at where the denominator is 0, 1/2 x minus 1 equals 0, that's going to be, if you just solve for x, you'll see that x is equal to 2 is going to give us an undefined point. So the domain, so this is also going to be the vertical asymptote. Hey, look, we already found it. So the domain would then be all x is such that x is not equal to 2. Okay, so there was a quick question in the chat of why I'm adding 2 to all the x values for this. Remember that this is essentially your h value is 1 and your b value is 1/2. So what you add to all the x values for the horizontal shift is h over b, which is 1/2, which is 2. Okay, so let's go on to the other stuff. X-intercepts. Okay, so let's figure that out. By the way, we already know the y-intercept because conveniently it just ended up being there. But anyway, so x-intercept then, we set the whole function equal to 0. So it might be easier than to, let's just do that out as much as possible. So 3/1/2 x minus 1 plus 2 equals 0, so that'll be equals -2. And then we can just multiply 1/2 x minus 1 to both sides. Then we get 3 equals, I'm going to need more space here, so I'm just going to move things around a little bit. So surprise, that's the next problem. Gonna move that. That's the graph paper layer, I think. Yes. Alright. Gonna move that then. Okay. So we have more space for this. Okay, wait, nope, not on the graph paper layer. Alright, so that'll be -2 times 1/2 x minus 1. So 3 equals -x plus 2. And then I'm just going to add x to one side and subtract 3. So we get x equals -1 is going to be your x-intercept. So it'll be -1, comma 0. So now we can plot that. -1, 0. And then the function is going to look something more or less like that. Alright, y-intercept we already found. Horizontal asymptote, vertical asymptote, they're already all found. Now we just need to state the end behavior. Oh, and then the range. So as x approaches infinity, y approaches something. Same thing as x approaches -infinity. Okay, so if we look at the graph, it's pretty clear that the function is just going to converge toward y equals 2. So, and that's going to happen both ways, right? So as x approaches positive infinity and negative infinity, y is going to approach 0. I mean, sorry, 2. Why did I put 0? And the range, if we look at the function, again, all we're doing is looking at the function. Is there any sort of restriction? Yes. The function is never going to touch y equals 2. Is your range always going to be related to the horizontal asymptote? No, because sometimes you'll have horizontal asymptotes where the function will go through it. So in this case, the range is going to be the set of y values such as y is not equal to 2. That's just what it's going to be in this case. So yeah, I'm going to give us, again, a little bit of time to process that, and then I'm going to give us another 7 minutes on the next problem. We're going to do that, and then we'll end the stream there. Going a little bit over time, but we did go a bit quicker and stuff in the earlier parts. Okay, at exactly 9:30, I'm going to start the timer for the next problem. So I'm slowly moving the thing down. That's the next problem. Alright, beginning the timer. Sorry, I didn't realize that the screen was not showing the next problem. Whoops. Yeah, when the timer runs out, I'm just gonna start going through it since, yeah, time. Alright, so now I'm just gonna go over this problem real quick. So, we look at this, it's not clearly a transformation of any sort, so let's just go through it, see what we get. Alright, so let's find the domain of this thing. Okay, set the denominator to 0, and then remove whatever makes that 0. So we get, let's see, that's gonna turn into x plus 3 times x minus 4. So the things that make that 0 are negative 3 and 4. So the domain would then be the set of all x values such that x is not equal to negative 3 and not equal to negative 4. Range, we'll find that later. Okay, anyway, let's see. X-intercept, Y-intercept. X-intercept is going to be, let's see, we set the top equals 0 because Y equals 0. So if the numerator is 0, the whole thing is 0. And then we can easily see that x equals negative 1/2 is going to make the top 0. So coordinate is negative 1/2, comma 0. Y-intercept, let's set the whole thing to 0. Y of 0 equals 1 over negative 12. In other words, 0 comma negative 112, 1 over 12. And then vertical asymptote. We found that there were two values that made the function undefined. So bring those ones down. We have two vertical asymptotes, x equals negative 3 and x equals 4. Okay, so then horizontal asymptote. Let's find that. So the degree of the numerator and denominator are different. The one in the numerator is less. Therefore, this is just going to be y equals 0. And then the end behavior. So there was a question before in class of how you know this is going to be the same as the horizontal asymptote. How you would kind of know that is mostly from experience, but also you can graph it and you can see. So let's just do that actually. And then I'm going to put a big red star right here so I don't forget the range too. And then, yeah, let's do it. Okay, so we're going to have to go to something with 4s. So let's just go by 1s again. 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. I think that went to 10. Just going to go up to the 9 part. Okay, so asymptotes x equals -3 and x equals 4. 1, 2, 3, 4. And then y equals 0 is our horizontal asymptote. X-intercept -1/2, comma 0. So, okay, that's interesting. This thing is on the horizontal asymptote. Is that okay? Yeah, that happens sometimes. And it's 0, -112. Okay, so it's like there-ish. Okay. So, that means if this... Notice that the x-intercept, that's going to have a multiplicity of 1. Because if you looked at this as a factor, multiplicity is 1. So it's going through the axis. And then it's definitely going to have to hit the y-intercept. And it's going to go like this. Since there's no other x-intercept, it's just going to go up. So is this all? No. So we're just going to reserve some space here real quick. And make sure we can see that. Okay, so scrolling that down. Okay, so let's look at what's going to be there. How can you figure out what's going to be here? Well, easiest thing is plug in points. So there's a bit of space up here. I'll do that. So x, y. What would you want to plug in? Well, let's see. We want to see what's happening beyond the -3 and beyond the 4. So let's just plug in something there. So let's see. Let's actually try to figure out if the function is positive or negative at those points. That's actually all we really care about because of the fact that if the thing is positive over in this area, if it's positive, it's going to be somewhere over here and going to look like that. If it's negative, it's going to be like that. How do we know that? We don't have any x-intercept here, so it's never going to hit the x-axis. So all we need to figure out is whether the thing is positive or negative. So let's just choose two values. Let's not table it. But let's just choose x equals -4, x equals 5. And use the factored form, which is 2x plus 1, divided by x plus 3, times x minus 4. This is going to make life really easy, actually. Because if we do -4 on the top, then we get something negative. Divided by -4 here is going to give us -1. So that's negative. And then -4 here is going to give us even more negative. So this is just going to be something negative. So from that, we can already tell that the function is going to look something along the lines of this. In that part, at least. Now let's test the other part. So if we have x equals 5, that's going to be, plug it in there, positive. Plug it in there, something positive. Plug it in there, we have something, again, positive. So we just get positive all around. Therefore, we're going to get something like that. So a lot of the time when you have test points like this, all you really care about is whether the thing is positive or negative. Obviously, you should check to see whether that's actually the case, like whether that's all you really need. But usually, yes. So how would you know? Just logic. If we look over here then, what we have is a graph where toward the infinities, as x goes toward both infinities, what's actually going to happen then is the function is going to converge toward that horizontal asymptote and just converge to 0. So in this case, we get 0 for both of these. Alright, And then finally the range, so that I don't forget it. What are the y values that exist in the function? Are any of them removed? Or does every single y value work? So range is a holistic review of a function. In this case, yes, there is that horizontal asymptote, and there are these two portions that are not touching it. However, this part in the middle goes through the whole thing, including the asymptotic point. Therefore, the range in this case actually is going to be all the y values where y is in the set of real numbers. Alright, so that's it, and yeah, so that's the end of the stream. I'll still be here if there are any questions, and then, yeah, so I'm currently recording while streaming, so I'm going to stop the recording. So if you're watching this on YouTube or watching, yeah, if you're watching this on YouTube, then it's going to be stopped from this point, so you're not going to hear any questions or anything from later on. You can always ask questions in the comments, obviously, and yeah, so hope this was helpful, and for those of you on YouTube, I will see you in the next video. Alright, so for those of you on Twitch right now, I'll still be here for a little bit, so if you have any questions, just ask them in the chat, and then, yeah. Alright, so there was a question about why it's okay for the function to hit the asymptote, the horizontal asymptote. The reason is because functions, I know that you're told usually the functions can't hit asymptotes at all, but a horizontal asymptote, remember, that just tells us where the function converges to. Therefore, toward the middle, you're actually able to hit that. That's fine. Okay, so I'm actually going to end the stream part right now, but I'll just still be here in the chat. If you have questions, just ask them in the chat. Alright, so thank y'all for watching, and see you later.